Okay, so we're going to uh, get into the idea of a fixed field, um, and this is the start of the Galois correspondence. Let me say fixed fields. And we saw in our motivating example, we saw that, but we're going to formalize it now. Okay, so just some definition here. So if L over K is an extension, then any field M such that K subset M subset L is called an intermediate field. Right? To as an example, real quick, actually, um, K is a subset of K is a subset of L, so K is an intermediate field. And so is L, as K is a subset of L, which is a subset of L. So you always have two, well, unless K is equal to L, you always have two intermediate extensions, always, unless it's a degenerate example where K equals L. And whenever we have an intermediate extension, so if K is a subset of M and a subset of L, then we can look at what we're going to call M star, which is the Galois group of L over M. And remember, what this is it's the set of all automorphisms such that sigma of M is M for all M and M. Okay? So we have to fix all of M pointwise. All right, so what do we learn here? Well, with this notation, K star is what? It's the Galois group of L over K. This is the whole Galois group. And what else do we learn? We learn that L star is the Galois group of L over L is the trivial group. Because I have to have an automorphism, but it has to fix everything in L, so it has to be the identity. It's a trivial group. And furthermore, M star being the set of all automorphisms that fix automorphisms of L that fix M, well, K is a subset of M. So if we fix little m in M, then we have to actually fix all of K too. So any automorphism of L that fixes M sits inside of the Galois group of L over K, because we not only do we fix K, we fix more than K, right? And so notice here that K was a subset of M, but when we go to groups, M star is a subset of K star. This behavior is called contravariance. So taking these Galois groups of intermediate extensions is contravariant. It reverses inclusions. So contravariance in general means sort of reverses arrows, but reverses inclusions is what it should mean in this class. Okay, so I said we were talking about fixed fields, and then I proceeded to not talk about fixed fields. So let's talk about fixed fields now. So what we've shown is to any intermediate field, we can construct a subgroup of the Galois group, this M star. I mean, that's worth writing down. Any intermediate field gives rise to a subgroup of the whole Galois group. Right? Now, what happens if we have a subgroup of the Galois group? Does that come from an intermediate field? So conversely, let's suppose that H is any subgroup of the Galois group. Then what? Well, we're going to introduce this. I think we've introduced this before, but I'm going to introduce it again, we're going to set H dagger to be the collection of all L's in L such that H of L is L for all H in H. That is, every element in this H dagger is fixed by elements of H. Remember, H is a subgroup of the Galois group, so it is automorphisms of L that fix K. But if it's not everything, or even in general, if the extension is not what's called Galois, you might fix less, right? If I have a subgroup, I might fix more than just K. I might fix, a larger set. So H dagger is a set of all elements in L that are fixed by every single element of H. Okay? And this is the fixed field of H. By the Galois action. And why are we justified in calling it the fixed field? Well, lemma. If H is a subgroup of the Galois group of an extension, then actually H dagger is an intermediate extension. So that means that K is contained in H dagger is contained in L. Proof. Since all elements of the Galois group fix K, K has to be a subset of H dagger. Because it's the guys that are fixed by just the elements in H. If I fix every element, if I fix all of K, if every element of the Galois group fixes all of K, then certainly the elements of H do. And by definition, H dagger is sort of naturally a subset of L. Why? Because it's the element of L such that a condition. So it certainly sits in between K and L. It remains to see that it's a field. So how are we going to do that? We're going to use the subfield test. Which was talked about in chapter 1. Okay, so we need to show that 0 is in H dagger. We need to show that 1 is in H dagger, why is 1 in H dagger? Well, sigma of 1 is 1 for any automorphism. So all automorphisms fix 1, period. We don't have to think about all the elements in H, just any automorphism has to fix 1. We proved that in chapter 1. So H of 1 is certainly 1 for all H in H. Thus 1 is in H dagger. All right, now we need to show that it's closed under subtraction. Let's take X and Y in H dagger so that H of X is X and H of Y is Y for all H in H. Then H of X minus Y is H of X minus H of Y, because automorphisms split up under subtraction. But H fixes X and Y. And that's true for all H and H. So H fixes X minus Y provided it fixes X and Y. So X minus Y is also in the fixed field. It's fixed by the action of H. And then division will be similar. I'm going to keep the same X and Y. H of X over Y is H of X over H of Y is X over Y for all H and H, provided Y is not 0, of course. So X over Y is in H dagger. So we're closed. We have 1. We're closed under subtraction, and we're closed under division. All right. Thus, H dagger is a field. In fact, it's a subfield of L because it passes the subfield test. So that's the fixed field, and that's why it's a field. So again, to recap, every intermediate extension gives rise to a subgroup of the Galois group, and every subgroup of the Galois group gives rise to a intermediate extension. There is a correspondence between the two.